Welcome to Griffin Pipe. We appreciate your interest in our products and hope you enjoy this plant tour. During the tour, we will look at the 5 major steps in the process of creating ductile iron pipe. As a quick overview, the pipe making process comprises melting, casting, annealing, lining and finishing, and quality control. Melting includes the conversion of reprocessed steel scrap into a base iron suitable for producing pipe. Casting utilizes a centrifugal process to spin molten iron into the proper size, thickness, and length. Annealing consists of a heat treatment to obtain the desired strength properties and ductility. Lining and finishing operations include the application of an internal protective cement lining and both internal and external asphaltic coatings. Quality control occurs throughout the process, from raw material to finished product, with strict adherence to industry standards. Dimensional, chemical, and strength properties are continuously monitored to ensure compliance. Griffin Pipe operates 2 manufacturing facilities in Lynchburg, Virginia, and Council Bluffs, Iowa. Lynchburg produces ductile iron pipe in 18-foot lengths for the 3-inch and 4-inch nominal diameter, and 20-foot lengths in sizes ranging from 6-inch through 24-inch nominal diameter. Council Bluffs produces 20-foot lengths in sizes ranging from 6-inch through 48-inch nominal diameter. Now let's start the tour. The melting process begins with raw materials, the main ingredient being scrap metal, primarily scrap automobile bodies that have been shredded to a usable size. The scrap metal is received throughout the workday by tractor trailers and is moved to the melting area by magnetic crane. The scrap is melted in a tall cylindrical furnace called a cupola. The cupola utilizes coke as a fuel source, and small amounts of limestone are added to help with removal of slag from the liquid iron. Coke is a byproduct of coal and is capable of producing the high temperatures and melt rates required for pipe production. To generate the high temperatures necessary to melt the steel scrap, hot, preheated air is continuously blown into the coke bed through openings called tuyeres at the base of the cupola. Batches or charges of scrap and coke are continually placed in layers in the top of the cupola to replenish the consumed fuel and melted iron at the bottom level where the melting occurs. The molten iron picks up carbon and sulfur from the coke before exiting the cupola through the tap hole. As the iron exits the tap hole, lighter impurities called slag rise to the top and are skimmed off. The molten iron continues down a trough into a large ladle where sulfur is removed by the addition of lime to the stirred molten bath. Sulfur removal is a key step in the production of ductile iron. The low sulfur iron flows continuously from the ladle into a large holding vessel known as a forehearth. The iron is poured from the forehearth into a large transfer ladle, which is transported by overhead crane to the plunging station, where a block of pure magnesium metal is lowered into the molten iron. The magnesium burns in a very volatile reaction, which serves to remove the oxygen within the molten iron. The combination of low sulfur and oxygen allows the graphite or carbon within the iron to form in spherical or nodular shape. The addition of magnesium is one of the major differences between the ductile iron of today and that of cast iron from years ago, where the carbon in the molten metal formed as longer flakes. Following the magnesium process, the treated iron is ready to be moved to the casting machines where the actual pipe is formed. Ductile pipe is manufactured using the Delaveau process, which consists of pouring molten iron of appropriate composition into a spinning horizontal cylindrical steel mold. Each casting machine is equipped with a pouring ladle. These smaller ladles hold enough molten iron to make several pieces of pipe before needing to be refilled. The machine operator places a sand head core into the bell end of the mold. Sand cores are formed from sand that is bonded together by a resin at an elevated temperature. This head core prevents iron from flowing out of the mold and also forms the bell and gasket seating area in the pipe socket. Sand cores are produced in a machine that is very similar to a large waffle iron. The sand and resin mix are placed into the core mold and heated to thermally set or harden the sand core. After approximately 1 minute, the mold is separated, the core is removed, cleaned, and ready to be used in the casting process. Cores are made specifically for the type of pipe being cast. Following American Waterworks Association standards, sand cores have markings which transfer to the pipe bell during casting. These indicate such things as country of origin, GP for Griffin pipe, the year of manufacturer, size of pipe, type of joint, and the allowable degree of deflection for the joint. Back at the casting machine, the pouring ladle tilts forward and iron pours down a chute and trough into the bell end of the mold. Once the socket is full of iron, the operator begins moving the mold assembly down the machine bed on rails, while continuously pouring iron and forming the barrel of the pipe. The centrifugal force of the rotating mold keeps iron against the mold wall as it solidifies. The forming process takes 30 to 90 seconds depending on the size and class of pipe being cast. You may have noticed the bumpy pattern which is called peening on the outside of ductile iron pipe. The peened surface on the inside of the mold allows the liquid iron to grab the surface of the mold during casting. If not for this peening, the iron would splash all over the mold, resulting in defects and scrap pipe. The centrifugal process is self-cleansing, in that any lighter impurities such as slag or gas are forced to the inside of the pipe barrel during casting, where they have no detrimental effect. After cooling in the mold, the remaining sand core is broken up and the finished pipe is extracted by a pipe puller mechanism. The hot pipe is then placed on rotating rollers to help maintain roundness and straightness prior to placement in the annealing oven. While still very hot, pipe is delivered to the annealing oven. Annealing is a heat treatment process that produces the desired mechanical properties of the ductile iron pipe. Annealing takes place in a very large natural gas-fired oven. The temperature at the entry point is approximately 1750 degrees. As the pipe moves slowly through the annealing oven, the temperature gradually decreases in the cooling zone to approximately 1350 degrees. The annealing cycle takes about 35 to 45 minutes. Prior to annealing, ductile iron pipe is fairly brittle due to the rapid cooling it experiences within the mold during casting. Without the heat treatment of the annealing process, the pipe would not have the correct properties and would easily crack. All pipe made by Griffin Pipe Products Company is manufactured and tested to meet or exceed all applicable American Waterworks Association standards. To ensure compliance with these standards, quality control measures are in place during all phases of the manufacturing process. The first step to ensuring a quality product takes place as the freshly melted metal pours out of the cupola. A sample is sent to the melting lab where it is immediately analyzed for correct properties. A second sample is taken after the desulfurization process, and another after the magnesium has been added. Samples are poured, solidified, and sent to the melting lab by a vacuum or pneumatic delivery system, similar to the type used at a bank drive-thru. Approximately 100 samples are taken each day. Samples are tested with a spectrometer and infrared analyzer for approximately 20 different elements to verify that these are at acceptable levels. Strict calibration standards are followed to ensure that the testing equipment is providing accurate results. Special attention is given to the possible presence of detrimental elements such as tin, copper, and chrome, elements that are not wanted in the final product. Personnel at each stage of the process within the plant have access to the information through computer workstations. Additionally, all labs have a camera view of the test results for the finished product. All of this helps each part of the plant better guarantee that highest quality pipe is being produced. It is after the annealing process that extensive inspection and testing of each piece of pipe occurs. Once the pipe exits the annealing oven, it is allowed to cool so that it may be handled and inspected by quality control personnel. Using flashlights and floodlights, inspectors look carefully for any obvious visual defects. Each pipe is subjected to a physical inspection and testing, which includes looking for obvious defects and gauging of the bells and spigots for proper dimensions. Pipe is also weighed to make certain that each class of pipe meets a minimum weight standard. If that weight is not met, it will be downclassed. If it cannot be downclassed, the pipe will be scrapped. Following weighing, pipe is barcoded with information regarding weight and class. Pipe is then subjected to a water pressure test, where water at 500 psi is piped in for 5 seconds. Samples of pipe are also taken at specific intervals to determine mechanical properties such as tensile strength, yield strength, elongation, and impact strength. The tensile test begins with a piece of pipe being trimmed off on the plant floor and being sent to the lab where a smaller sample bar is cut out. The bar is placed in a lathe and machined down to a required diameter. Next, it is placed in a tensile testing machine, which will apply a tension force or pull to each end of the specimen. The sample should remain elastic to a minimum strength of 42,000 pounds per square inch of tensile force. The test continues as the specimen passes its elastic strength region and proceeds to its ultimate tensile strength, which must meet or exceed 60,000 pounds per square inch. After this point, the sample will begin to stretch and eventually break. The sample halves are put back together, and the distance between the two gauge points is measured. The tensile specimen should have stretched at least 10% to comply with standards. The strength grade properties are typically recorded as tensile yield elongation, or as an example 60-42-10. This shows that pipe is meeting or exceeding the standards set forth by the AWWA. In the Sharpie impact test, a small sample is removed from the pipe and is cut and machined with a small notch in its middle. It is placed in an impact test with a swinging hammer. It should not break below 7 foot-pounds of absorbed energy at room temperature. This test requires temperature controls in order to properly validate the tests. The Sharpie test is performed once every hour of production for each size of pipe. One Sharpie test must be run at -40 Fahrenheit to ensure that brittle fractures occur well below the expected temperature range experienced by ductile iron pipe. At this temperature, the sample should not break below 3 foot-pounds. In addition to testing required by AWWA, Griffin Pipe Products also performs more specialized tests including microstructure examination, hardness testing, and ultrasonic velocity testing. The microstructure test involves taking a punch or sample from the spigot and placing it in a microscope to examine closely the microstructure of the iron. The microstructure and hardness will determine if the annealing process has been properly performed. It also allows examination of the shape of the graphite nodules, which should be nearly spherical and well distributed. Pipe which fails any of these tests may be re-annealed. However, if the desired microstructure and mechanical properties cannot be achieved after re-annealing the pipe, it is scrapped. Pipe which has been inspected and passed by quality control is marked with the class of pipe, date of casting, and additional information. The pipe then moves down the line to be finished. Finishing involves lining the interior of each pipe with cement mortar and then applying a thin asphaltic coating on the exterior and interior. The purpose for lining ductile iron pipe is to provide a barrier to prevent buildup of corrosive products on the wall of the pipe. Cement lining is similar to the casting process in that the pipe is rotated and centrifugal force is used to apply the cement to the wall of the pipe. Prior to entering the cement application area, special caps are placed on the bell and gasket ends to make certain the pipe is properly lined. As pipe is rotated, a pre-mixed batch of Portland cement mortar is fed down a long trough that extends to the far end of the pipe. The mortar deposits on the surface of the spinning pipe as the trough retracts. Following application of the cement lining, the pipe moves to a high-speed spinning station, which rotates the lined pipe with even greater speed to make certain that a good, tight, smooth lining is achieved. This has the effect of compressing the cement lining and forcing any water to the surface where it can be rinsed out. After the lining process, any remaining loose cement is rinsed out and the pipe inspected. To help retain moisture and ensure proper curing or hydration, an asphaltic paint or seal coat is applied over the still damp lining. This also helps prevent flash rusting that would occur on unpainted pipe. Both the inside and outside of the pipe are painted at the same time. Once painted, the pipe is bundled and allowed to cure for a minimum of 24 hours, after which it is ready to be shipped. However, just before loading a truck for shipment, finished pipe has one more stage of quality control. A final visual inspection and a reverse piece of duct tape is used to determine that the seal coat is properly set. Pipe is then loaded up to be sent to job sites across the country. We hope this plant tour has been both interesting and informative. Griffin Pipe Products Company is committed to exceeding customer expectations by delivering the highest quality product at competitive prices and with an ease of purchase that is second to none. Griffin will continue to emphasize the highest level of integrity and operate with the highest ethical standards. Thank you for your interest in our company and our ductile iron pipe products.